I'm going to be talking about the emerging science of benchmarks, and this talks about why machine learning as a field, as a scientific discipline, seems to make progress. And so it makes sense to start with a little bit of philosophy, because philosophers have thought a lot about, like, you know, how does science make progress? Is there a scientific method? Is there some sort of logic behind science? And the philosopher Paul Feyerabend famously held that the answer is no. And he argued that the only principle that does not inhibit progress is anything goes. Okay, so science doesn't follow sort of any particular logic, and the only way you can't stop science or slow it down is to permit some kind of anything goes. And if you look at machine learning in the last sort of 80 years, since the sort of neural networks era of the 1940s, you would think that Feyerabend was kind of right. You know, machine learning has really sort of embraced the anything goes. It's a discipline where you can do and try out pretty much anything. And it's actually something that drew me to machine learning, because you can really kind of do whatever, and it's a very liberating field to work in. You could be inspired by the human brain, or by child development, or by physics, or anything you want, and you can throw spaghetti on the wall and see what sticks. But there's one thing that you need to make this work, and that's the idea of a benchmark. It's the one rule that we have in machine learning to tame the anything goes that we do. And so the way this plays out in machine learning, you know, is what follows from the iron rule. That's a term that the philosopher Michael Strevens coined in his book Knowledge Machine, and it states that all disputes between scientists must ultimately be settled by competitive empirical testing. So you can do whatever you want, but at the end of the day, you must come together in some coordinated way and competitively test what's best. Okay, in machine learning, the way we do this is we agree on a metric, could be accuracy, error rate, various things that are relevant to your application. We agree on benchmark data. So it's a data set, a set of test cases that we think is relevant for what we're trying to do. And then we compete. And we tell the community, just go ahead and you knock yourself out, do whatever you can to optimize the metric on the benchmark data. Okay. So we call this a benchmark, and it's the main scientific paradigm in machine learning. It's how the community clocks and how it works. And everything, all the progress sort of hinges on this one idea. So what's interesting about this idea is it kind of emerged, okay? It wasn't there from the beginning. It's not like the founding figures of machine learning sort of sat down and said, here's how it's going to be. We're going to proceed by this idea of a benchmark, and we're going to figure it out this way. Benchmarks didn't follow any sort of theory, at least none that we recognized a priori. We didn't know what we're doing when it started. And so looking a little bit at the history, you know, it goes back much further. In fact, it goes back to the 50s. But it really kicked off in the 1980s when DARPA grant managers decided that benchmarks were a great way to evaluate scientists objectively according to some quantitative criteria and decide who should get money and who did well on their grant proposal. And then became a major academic idea, benchmarks in the MNIST era, the character recognition data set that fueled some of the early advances in computer vision. And it really rose to a new level of popularity in the ImageNet era that is kind of co-constitutive with the deep learning revolution of the 2010s. And everything we did in the 2010s was sort of optimized for and against ImageNet, so it was really sort of heavily used in the development of deep learning as we know it. And I'd argue that today we're in a new era. It doesn't yet have a word, so I call it the polymorphic era, because benchmarks are sort of taking on a lot of different shapes. Okay, we're seeing a plurality of benchmarks and also lots of different ways that people try to do benchmarking. So there are new kinds of benchmarks that we're looking at. They're trying to grapple with the fact that we now have these large language models that seem to be a little bit different than what we're used to. So I'll be talking about this. Here's the plan for the talk. I'll give you an outline of the science of benchmarks. Where did it come from and what do we know? I'll draw some scientific takeaways from the ImageNet era with the benefit of hindsight. What did we learn from ImageNet in the 10 years of using it? And I'll move into challenges with the era of large language models and why it's so challenging from the perspective of benchmarking. So we'll see some very recent work in that area. And I'll argue that we really need a science of benchmarks, and I hope that you guys will all join this sort of effort in thinking a little bit about sort of the underpinnings, the scientific underpinnings of this thing that we sort of take for granted and all do every day. All right, so how did it start? How did the science of benchmarks start? I argue it started with a mistake. It was a good mistake, but it was a mistake nonetheless, and here's the mistake that sort of started this all. It was the mistake to assume that benchmarks are just the holdout method. How many of you have heard the word holdout method in some formal way? Jelani has heard of it, good. And so it's basically, it goes by many names, cross-validation and other things, and I'm just referring to the most basic version, the most vanilla version, where you split your data into training set and test set, and you set aside the test set, and you apply the anything goes principle on the training set. You just tell people you can do whatever you want with the training set, no constraints there. But then in the end, you rank the models that were proposed on the test set. Okay, that's the holdout method. And I say in the end, because that's really what the statisticians recommend you do, okay? So if you go to your favorite stats textbook, like, Elements of Statistical Learning, there is a passage about the holdout method that says very clearly that the test set should be kept in a vault and be brought out only at the end of the data analysis, okay? So ideally, you should do all the model building up front and use the test set only once at the end to rank all the models. That's the idea behind the benchmark method, the holdout method. And the reason why you do this is because then you can prove lots of theory about it using concentration inequalities. You can do things like saying that the number of models you can test on the holdout data is exponential in the size of the holdout data, okay? So you just, by concentration inequalities, if you fix the models up front and then you sample your data, you get concentration, and you get all sorts of amazing theory, and you can prove that you can test exponentially in many models on a data set of size n, okay? This just follows from concentration inequalities and the union bound. So the theory that we know for this holdout method all hinges on sort of like doing the model building up front, then sampling the data, and then evaluating the models. But let's look at the empirical reality of machine learning, which is kind of, how the machine learning community actually uses the holdout method. In this case, the test set is sort of in an ongoing feedback loop with the community, right? So like a researcher proposes a model, evaluates it on a test set, gets some feedback, the feedback gets published in papers, or we rank models, public benchmarks on Hugging Face and other leaderboards that are public, so we publish the results, and we continue. So the holdout method, the holdout data is sort of iteratively used, incrementally used to build better and better models, and that's the whole point of how we do machine learning. So we incrementally use the data. Okay, so just to convince you how much we use benchmark data, the MMLU language model benchmark, so that's a math multiple choice question answering benchmark called MMLU. It has 14,000 questions in it, and as of April 2024, it got 5 million downloads per month on Hugging Face. All right. I did the math. That's 60 million downloads per year. Okay. So 60 million downloads per year for just a single benchmark data set. That's not all that large. And if you think that every download is at least one evaluation, which I think is fair to assume, then this data set is getting millions of evaluations every year from the machine learning community. And so machine learning is really adaptive. Prior results inform later work. We work with the holdout set. We don't just set it aside in a vault. We really have it sort of in our model building loop. And so one thing that we realized about 10 years ago is that adaptivity, this kind of adaptively working with data, breaks all existing statistical guarantees of the holdout method. Okay? And in fact, you can show very easily that in this adaptive model of using the holdout data, you can at best get linear longevity. So after a linear number of evaluations, you've burned through your holdout data and it's worthless, okay, at least in the worst case. And so this observation launched the research area of adaptive data analysis, with joint work with Cynthia Dwork, Vitaly Feldman, Tony Pitassi, Omar Reingold, and Aaron Roth 10 years ago, which started my interest in benchmarks, because I thought that based on these observations, that machine learning was headed for some kind of scientific crisis. That it was going to go off a cliff where we're going to overfit to all these benchmark data sets, and we're going to have a scientific crisis like social psychology or like other disciplines that ran into issues like p-hacking. I thought the same thing was going to play out in machine learning. But time proved me wrong, okay? So let's look at what actually happened and how much benchmarks have sort of been used and what kind of longevity they have in practice. So here's a plot from Papers with Code, and that sort of tells you all the papers that have published results on ImageNet and the numbers that they have claimed. And here's the top one accuracy as it evolves over the years. And you can see that up until a couple of years ago, ImageNet was still very actively used as a computer vision benchmark, and people continued to improve strongly in terms of accuracy on ImageNet. Okay, so ImageNet supported over a decade of active model development. There were fundamentally new techniques coming out 10 years after the data set was proposed. But should we trust these model rankings? Should we trust sort of the ranking of like what's the best model, what's the second best model, and so forth? if really we've been using the same data set that was publicly on the internet for all those years? Or have we overfit to ImageNet? Okay? To find out, researchers created a fresh test set for ImageNet by painstakingly following the original sampling process for the ImageNet test set. And they found out that on this fresh test set that they created, the model ranking was preserved. The accuracy numbers dropped, but the model ranking was preserved. So the ranking of the models that had been developed on ImageNet was actually stable. It generalized to this new test set that was created. And the same is true for MNIST. I think Leon Batou found some hidden MNIST digits or lost MNIST digits in some drawer, and they reevaluated all the MNIST results on the lost digits. The paper's called The Lost Digits. It's a beautiful paper. And they found that even on MNIST, this thing that everyone calls a toy benchmark and it's been overused in like 20 years of MNIST, even there, the model rankings are stable. The model rankings hold on the lost digits. Okay? Same for Kaggle competition, same for like language model benchmarks like Squad. So what's going on? There seems to be this empirical phenomenon that I call the internal validity of the iron rule, which is a fancy way of saying that beating the previous best repeats or replicates in similar conditions. So if you go from like one data set to some very similar data set, you expect to get the same model rankings. Okay? This is a robust empirical finding at this point. And so we tried to do some theory explaining why you get this kind of validity, why you get this sort of generalizability from one data set to similar data sets, or the same, more draws of the same data set. And so one reason for this is actually, again, the iron rule. And we can turn this iron rule that I mentioned, beating the previous best, we can turn that into mathematical assumption. And we can say that let's assume that researchers only care if they beat the previous best. So the only way mentally you access the holdout set is by checking if you beat the previous best. And if you didn't, you forget about it. And if you did improve, or if you didn't beat the previous best, you publish your result. Okay? So you only publish results if you beat the previous best. Let's make this our assumption. Then you can show, and this is a work with Avram Blum from several years ago, you can show that under this iron rule assumption, the benchmark data set again has exponential longevity. So you recover the results that follow from the iron vault assumption under this iron rule assumption. Okay? So this assumption of competition or the iron rule is nearly as good as locking away the test set altogether. So this kind of blew my mind when we proved this, because it showed that the fact that we compete over these benchmarks is a very strong regularizing force that actually promotes scientific validity that you otherwise wouldn't have. So the seemingly narrow way of proceeding by only caring about the previous best, that's actually a blessing from the perspective of preventing some kind of scientific crisis. You can use this result prescriptively as like sort of a way of limiting feedback in a competition and saying I'm only going to like release feedback to you in my competition if you actually beat the previous best. But I prefer to think about it as a postulate about the community, as a way of understanding the machine learning community. And I think of the iron rule as like a way that we work. And this way that we work seems to imply something about progress and the robustness of progress. Okay. So I call this like an instance of the socio-technical forces behind benchmark longevity. Okay, there are all these reasons that we discovered in the years after of like why benchmark data sets live longer than we had reason to believe at first. Competition is the one I just mentioned. Collaboration also works. The fact that we all share code and that we try out things that are very similar, that have very similar priors, that also seems to promote benchmark longevity. Even the cognitive and behavioral biases that data scientists might have, things like anchoring bias and similar things that are about our cognitive limitations, they can actually promote benchmark longevity. And some mundane data set artifacts that you find in ImageNet, like the fact that it has 100 very similar dog breeds, that can also promote benchmark longevity. And the thing I want to highlight, so all of these give you internal validity of benchmarks, right? They give you like this internal validity principle. And the thing I want to highlight, these aren't purely statistical assumptions. These aren't purely mathematical assumptions. These are in some sense like assumptions about how the community works, okay? So you need to think a little bit about the dynamics of the community to understand why the holdout method works. Okay, so we know in both theory and sort of from empirical work that model rankings seem to be very robust in the sense that they replicate under similar conditions. They have internal validity. But let's ask a more daring question. Let's ask, do model rankings replicate under radically different test conditions? let's say instead of going to similar test conditions, I go from one domain to an extremely different domain, like a data set that's sort of very different from the one I started with. Do we expect to see the same rankings? Or does sort of the benchmark paradigm break down when we go from one domain to a very different domain? All right? So to find out, we designed something called the image not experiment. This is work with Olav Alessalo-Dean from like a year ago about, he was an intern at MPI. And so we proposed ImageNot, which you can think of as an anti-replication of ImageNet. So it's basically a data set of the same scale and diversity as ImageNet, but it's different in every other regard. So we try to make it as conceivably different from like ImageNet as possible, while maintaining sort of the same scale and diversity. So same number of data points and the same number of classes as ImageNet. So or the test set has 50,000 data points and 1,000 classes, okay? And so, whereas ImageNet was carefully curated by humans with multiple annotators per image, many of you know this stuff, it had to be 9 out of 16 annotators agreeing on the candidate images, and only then was it included in the test set. ImageNot is just a quick and dirty web crawl. It's just based on like dirty web data where we just select images based on their captions and like how similar the captions are to the class name. So, and then what we do with this data set, which is really just, it's kind of a junk data set, it's just a quick and dirty web crawl data set, we retrain key ImageNet era models from scratch. So we take all the models that had been proposed from the ImageNet era, about 10 or so, the key sort of advances, we retrain them on ImageNot, and we see what happens. Okay, so what happens? Are the model rankings preserved now that we retrained all these models from scratch on ImageNot? Okay, so the answer is yes. Okay, so in fact, the rankings are preserved exactly. ImageNot has exactly the same rankings as ImageNet. And what is perhaps more striking is that the relative improvement in accuracy that each model makes relative to the previous best earlier model is roughly the same on the two data sets. So you get the same relative increments in accuracy going from one model to the next model in the course of time. So the improvement that VGG makes over AlexNet is about the same on the data set. The improvement that ResNet made over Inception is about the same, okay? And so you get this like really interesting phenomenon that even quantitatively the relative increment is the same. The accuracy numbers are very different, of course. Like ImageNot is much more noisy than ImageNet, so the accuracy numbers are generally much lower and don't look like they have anything to do with each other. But the relative improvements are the same, and as a result also the rankings are the same. So how did we create ImageNot? Just a quick sort of plug about this. We started from the LION database that many of you know. It's a fantastic repository of about 6 billion image caption pairs. So every data point in LION is a URL and a caption. The URL points to an image. You can crawl this or you can search this data set. And so what we did is we just picked 1,000 arbitrary classes, class names, while avoiding all the ImageNet classes in the WordNet hierarchy. So ImageNet comes from the WordNet hierarchy, and we avoided all the classes that are in the ImageNet data set, try to be as far away from them as possible, but picked arbitrary class names subject to that constraint. And then we selected images from LION based on just text similarity between the class name and the caption. That's all. Using just a Roberta model, so no modern language model or anything, just an old language model with similarity between the class name and the caption. That's all we selected this. There were some additional safety filters to make sure this is a reasonable data set, but that's all we did. Okay, no annotators, no label cleaning. Very messy data set. And this built on some earlier work with Ali Shirali where we did something very similar. Just to convince you how different these data sets are, let's look at some of the images. I'd like to visualize this to really see how striking the differences are. So here's a typical class in ImageNot. It's called cleats. So what are cleats? Well, cleats are the things that you might see on football shoes. Okay, but also in this class there are lots of images like football players that might be wearing shoes with cleats, but you don't actually see the cleats in the picture. So it's very messy. Or you get something entirely different, like the things that go on bicycle shoes, which are also called cleats. All right, so you see there's like not a lot of like sort of similarity between these images. There's another class called batter, which could be a cartoon about a batter, or it could be like dietary advice, like you should always batter your chicken for better flavor. Or it could be like something entirely different, like a cosmetic product called Batter Up. Okay, so you see ImageNet classes are very diverse, they're very messy. Humans probably wouldn't exactly agree on what the class name is for this, and so on. And contrast this with ImageNet. Well, I don't know if you still remember, who remembers ImageNet? Whoever looked at ImageNet? Have you actually looked at the images in ImageNet? No one? There, one person has looked at the ImageNet pictures. Okay, more people, all right. They're all dogs, okay? So they're actually all dogs. So ImageNet is all dogs. And so not only is it all dogs, like every dog class, like Irish Terrier, is front and center in Irish Terrier, okay? It's not just like sort of an Irish Terrier somewhere in the picture. It's like front and center in Irish Terrier. This is what an Irish Terrier looks like. If you go to Blenheim Spaniel, I didn't know what that was, but there's a dog called Blenheim Spaniel. You get front and center Blenheim Spaniels. Apparently, mechanical Turkers know how to identify a Blenheim Spaniel, and they agree that this is a Blenheim Spaniel, and they all look, you know, front and center, the dog, nothing else. Maybe another dog in the picture, but humans have to sort of agree that this is the thing that's in the class. It's completely different. These data sets are completely different, and yet they give you the same model rankings. I find this mind-blowing, okay? So what can we learn from ImageNet? I suggest, or this is like a conjecture maybe at this point, that there is sort of a principle of external validity of the iron rule. That if you beat the previous best under sufficiently general conditions on a big enough, diverse enough data set, it will likely replicate elsewhere on other big enough, diverse enough data sets, even if these data sets don't have anything to do with each other. So it's a much stronger principle that might be true about the validity of benchmarks than we had previous reason to believe, okay? In fact, this gives you evidence that ImageNet could have been anything of similar scale and diversity. If you had gone back in time to 2012 and you had replaced ImageNet with ImageNot, you still would have gotten the deep learning revolution, okay? The deep learning revolution would have happened on this, you know, junky web crawl data set. It would have still happened, okay? So this is fascinating to me. And we don't even need clean labels, okay? So you don't even need clean labels to have a good benchmark data set. There was all this like discussion of like the importance of high quality labels on ImageNet and had to be 9 out of 16 annotators and so on. You don't even seem to need that to get a good benchmark data set. I found this so surprising that a student and I looked at this claim a little bit more deeply from a theoretical perspective, and we proposed a model of benchmarking with noisy labels. That's very simple, and some of the theoretical folks in the room might really appreciate this. So it's a very basic problem, which is you're given two binary classifiers, F and G. Which one has a higher accuracy? And you're just trying to identify which of the two has higher accuracy. So what are you allowed to do? You can draw an unlabeled data point X for free. Unlabeled data is free. And you can get a label for, let's say, $1. Okay? You can draw an unlabeled data point for free, but labels are costly. Labels cost $1. So getting labels is expensive. And moreover, labels aren't perfect. So annotators make an error with some probability p less than 1/2. Okay? So the label is noisy, and with probability p less than 1/2, it's incorrect. Okay? So now here's the basic question. Let's say you have $10,000 and you're trying to create a benchmark data set. How should you best spend your budget? Here's the standard idea that people have, and that's sort of the ImageNet strategy. You sample, let's say, 2,000 unlabeled data points. And for each of these 2,000 points, you sample 5 independent labels. So that sums up to $10,000. So you spend your budget. And then for each data point, you take the majority vote over the 5 labels. Why? Because the majority cleans up the labels, okay? So the majority label is much cleaner, is much less likely to be wrong than each of the individual labels. Okay? So there's some kind of data cleaning strategy. And so you can ask, is this best, or what is best? What is the optimal value of k? In this very simple mathematical model, what is the optimal value of k? How many labels should you get for each data point? We prove that in all cases, it's best to sample n data points with only one noisy label each. Okay, so the optimal k is always 1. Okay, so it never makes sense from the perspective of identifying the better classifier to clean your labels. It's always wasteful to do that. Florian, my collaborator, wanted to call this paper all the single labels. I stopped him from doing that. But this is what it says, okay? A single noisy label per data point is best, okay? Being an advisor is hard sometimes, okay? You have to shoot down ideas like this. But this is what the theorem says, and we didn't find a simple proof. I think there should be a simple proof, and I hope one of you will find a simple proof, but it wasn't, in the end it was kind of a grind, and it's sort of long, tedious proof based on Kramer's theorem, and I feel like one of you should look at this and tell us what the right way of doing this is. But basically, we sort of compute an exact asymptotic tail bound on the probability of not identifying the better classifier. And then we extend that to many model comparisons via the union bound if you want. And there's a kind of a subtlety here because you could also ask what's best for multiple comparisons. That's not necessarily the union bound. Okay, so there's like an interesting question here of what's the optimal thing to do when you're not applying the union bound, but you sort of want to know it's optimal for multiple comparisons. And it may not be the union bound. So our result is really only the optimal thing for two classifiers. Technically speaking, we don't know what the optimal thing is if you're comparing many classifiers. Anyway, you can use this as an alternative to Hoeffding's bounding. You can use it for sample size calculations. So we have a little sample size calculator. If you're designing like a benchmark and you have annotator errors, you can use this to compute the optimal sample size that you need. And you know, it gives you a nice, we sort of implement a nice fast way to compute the optimal bound. Okay, so let's move on. Let's leave the ImageNet era behind. This was sort of the era where we knew what things meant. You know, things were relatively clear. And let's enter the more confusing, but also very interesting polymorphic era. And I tortured Google Gemini, the plugin in Google Slides, for an hour to get this picture. And it's my rendition of the polymorphic era. All right, so this is how I feel about benchmarking right now. We don't quite know yet what we're looking at. All right, is this a bird? Is it an elephant? We don't know, okay? It's happening. It's definitely happening in front of our eyes. Something is happening, but we don't quite know yet what's going on in this era. So why is this new era of like large language models so challenging for benchmarking? Why is this such a different from the old days? There are four major challenges that I'm going to tell you about in the next 20 minutes. And each of them is sort of one reason why this is tricky, okay? So first of all, models have many capabilities. Instead of having just an image classification model, we now have these generalist models that are expected to perform at many very different tasks: math and sentiment analysis, facts and poetry, you know. So very different tasks that don't have any similarities. And so people have proposed these multitask benchmarks as a way to reliably test sort of all these capabilities at once. And I'm going to ask if that can work, okay? If multitask benchmarks really sort of achieve the promise of holistically evaluating these kind of models. The other issue that we're facing is that these models evolve very rapidly and that it's hard for benchmarks to keep up. So in response to that, people have proposed dynamic benchmarks, which sort of grow and get more challenging as the models improve in capabilities. And we'll ask if these things can work and if they do their job. The other issue is that models have seen the internet. And if models have seen the entire internet, it's a very good question to ask, what if they already trained on data sets or data points that look very similar to our benchmark data, okay? What if we're testing them on something that they more or less have already seen, or at least similar things, okay? And we'll see how to cope with that. And finally, I'll end on a note of what if models exceed human capabilities? What if we have to sort of evaluate models at the frontier where the new models that are coming in actually are better than the human experts or the human annotators? Can we, in that case, use models for self-evaluation to get sort of reliable insights about benchmarking? Let's start with this, multitask benchmarks. And it's very helpful to think of multitask benchmarks from the perspective of social choice, because you can think of these different tasks as voters. I guess that's a very timely example. And you can think of the models as candidates, okay? So you can think of each model as being a candidate that the different tasks vote on. And a benchmark in this view is just a voting rule that has to aggregate many rankings into one. Okay, so you already see that this is kind of a challenging problem. You have all these different rankings coming from these different tasks, and you need to produce a single ranking which gives you a good assessment of model performance. There are lots of things. There are cardinal benchmarks, which do things like average out accuracy numbers, so they aggregate numerical scores. And there are ordinal benchmarks, which don't sort of average out any numbers, they just work from rankings. That's why they're ordinal. So they just work from like winning rate and things like that. So how often you come out on top in a ranking. So those are ordinal benchmarks. One of the ordinal benchmarks that's quite popular is HELM, Holistic Evaluation of Language Models. It's run at Stanford and is one of the standard benchmarks. And what they do is they look at the mean win rate. So that's the average quantile your model has in the different task rankings across all tasks. So you can think of this as the mean win rate. It's like how often, or the chance at which you win a model-to-model comparison. So that's ordinal. You can compute that from just task rankings. You don't need any numbers for it, which is appealing. And then there are things like cardinal benchmarks, like the Open Language Model Leaderboard, hosted by Hugging Face, where you just average out the accuracy numbers, so that's a cardinal benchmark. So both of these things happen. So we looked at this from the perspective of social choice, as I said, and there are lots of impossibility results in social choice. There are lots of results saying that, you know, aggregation is hard, and there are also there are things that you can't achieve. There are multiple properties that you can't simultaneously have, okay? So we noticed that there's a pretty big stumbling block here, and it's sort of inspired by Arrow's impossibility theorem. We introduced two key properties of multitask benchmarks. One is a property that you want, and we call that diversity. And diversity is basically just variance in the rankings. So it's something desirable. Because you're designing a multitask benchmark, it better be that these task rankings are diverse, that they measure different things. So diversity is just variance in rankings. And the other property, which is something you don't want, is sensitivity. And that's sort of asking how much can irrelevant changes to a single task affect the overall ranking. Things like, let's say I introduce a weak model to the benchmark. Can it overturn the overall ranking? Or let's say I replace one task by an equivalent task by sort of rescaling the metric in a monotone way. Does that somehow affect the overall ranking? So these are relevant changes. They shouldn't matter because they don't change the individual task ranking, okay? But do they change the overall ranking? And so our key finding, it's an empirical finding, but I would love to see some theory on this, is that the more diverse a multitask benchmark, the more sensitive it is to irrelevant changes. Okay, so the less robust it is. So you can make benchmarks more, you know, diverse, but you pay in terms of sensitivity. And the picture is quite striking. Here is a plot of major existing multitask benchmarks, where on the x-axis you have diversity, on the y-axis you have sensitivity, and you can see that all existing multitask benchmarks fall on a line between a constant benchmark, or a single task benchmark that just says one ranking, and a random benchmark, where you just have a bunch of tasks with random rankings. And all the tasks fall on this line between constant, has zero diversity and zero sensitivity, and random, which has high diversity and high sensitivity. And so you might notice that I included ImageNet here. That seems confusing because ImageNet is not thought of as a multitask benchmark. And so what did I do here? Well, it sort of served as a sanity check. We took ImageNet and we created a mock-up multitask benchmark by taking the ImageNet classes and partitioning them into 20 random tasks. Okay, each group in the partition is a task, and we sort of call this like a multitask version of ImageNet, and we see what it is, or where it clocks in on this plot. And interestingly, these measures of diversity and sensitivity correctly identify that it's still a single task benchmark. So you can't sort of trick these measures by you know, disguising a single task benchmark as a multitask benchmark. So you really have to try something else, and these benchmarks are more diverse, but they're also more sensitive to relevant changes. So diversity comes at the cost of sensitivity, and just to give you a sense of how striking the situation is, here's how much we can perturb the actual rankings on existing benchmarks by just completely irrelevant changes, things that definitely should not matter for the benchmark. You can overturn these rankings quite a bit, and you can mess them up quite a bit. Okay, so on the left, you always have the original ranking, and then you connect it to where it clocks in afterwards. Okay, this is how much sort of you can shake up these rankings by just irrelevant changes. If you have a multitask benchmark and you want to try out see where your benchmark clocks in, we wrote a package called BenchBench. You can pip install BenchBench to play around with this and see where your multitask benchmark comes in. If you find something interesting, let us know. Okay, so if you find a multitask benchmark that sort of avoids the line and has some like really interesting trade-off between diversity and sensitivity, I would love to know. So please let me know if you have something like that. But with that, I want to move on to dynamic benchmarks. There was another fascinating sort of idea in this new era. And it started several years ago at Facebook with a platform called DynaBench that I thought was really exciting and really interesting. And it was sort of a platform for dynamic data collection and benchmarking. And it sort of was trying to address all sorts of issues with static benchmarks like ImageNet. So they argued that these static benchmarks, they have well-known issues, they saturate quickly, they're susceptible to overfitting, they contain annotator artifacts, and et cetera, other issues with them. And so they wanted to have a benchmark that improves with the models that you built. So here's what they proposed. They said, how about this? Start with like initial data. Give that initial data to your model builders. So invoke the community as like a risk minimizer. So let the community build models on this. and then take the best model that they found and identify failure cases of that model, that's called adversarial data collection, and throw these failure cases into the data pool and continue. Repeat the model building step and continue go on with that iteration of model building and adversarial data collection. And hopefully that will continually improve. And it made a lot of sense to me because a little bit like boosting, you train on your errors, you identify the errors and then you train on them and hopefully you get better. So that seemed very reasonable to me. And so we wanted to know if you can actually prove that this works, if something like that could work. And we proposed sort of a theory of dynamic benchmarks. This work with Ali Shirali and Reddy Adebebe from a couple of years ago. And we created a model of dynamic benchmarks, which just says a dynamic benchmark is a DAG, a directed acyclic graph, with 4 operations. So it's very simple. The operations is model building. You can go to the community and you can say, find a good model, okay? You can ensemble models that people have found into one model, so model assembling is fine. You can collect data using adversarial data collection, so you can find failure cases of any specific model, and you can pool data, so you can take whatever data sets you found and you create it and create a new data set out of this. So the proposal by Facebook is just the standard design. It's a directed path that alternates model building and adversarial data collection. But the model permits for many other things that you could try out, okay? So what we showed, unfortunately, is that the standard design, in the standard design, progress will stall after 3 rounds. So there's no reason to believe that progress will continue after just 3 rounds of the standard design. And in fact, that's consistent with what they observed empirically. So typically, performance in dynamic benchmark seems to plateau after about 5 rounds or so, okay? So this seems to be what's also happening in practice. Ali came up with these incredible, hierarchical dynamic benchmarks that he invented that guarantee provably strictly more progress than the standard design. So there's something more clever that you can do, but they're also much harder to implement. So again, if the theoreticians here, you look at this and you find something amazing, I think it could have a lot of impact. So I would love to see more work on trying to find the right way of doing dynamic benchmarks. It would be nice if we could do it. It's an interesting proposal. Okay, so there's another big issue with model evaluation in this new era, which neither multitask benchmarks nor dynamic benchmarks could possibly address. And so let me, to sort of motivate this issue that we haven't addressed yet, let me talk about an empirical puzzle, okay? So, it's late in the talk, but look at the following plot and tell me what's going on. So this is again MMLU, so math questions, question and answering. And I'm looking at what's called a scaling law. So I'm looking at pre-training compute, how much pre-training compute the model had, versus how much accuracy it gets on MMLU. So every dot here is a model, and I'm looking at how well models translate compute, so how large they are, scale, to accuracy. And I'm contrasting older models with newer models. So the blue dots are models that were trained before November 23, and the other models are trained after November 23. So orange dots are newer models, blue dots are older models. Jelani, what do you see? What do you see? Which is better? Which dots would you prefer? Okay, so if Jelani doesn't know, that's an alarming sign. But if I look at this, it would seem to me like the newer models are better, okay? So let's make this a little bit more clear. It seems that newer models appear to better leverage pre-training compute on MMLU compared with older models. All right, so let's look at this and look at the regression lines that I can draw here. So it seems that the orange dots are generally above the blue dots in the sense that for a fixed amount of training compute, the orange dots are more effective and get higher accuracy. So if I'm willing to spend, let's say, 10 to the 23 flops, then the orange line is better than the blue line. So newer models appear to have 7% more accuracy on MMLU for the same amount of compute. So that seems good. It seems that newer models actually are more efficient. There was progress in the community, so we're building better models now. The newer models seem to be just more effective at getting higher accuracy out of the same compute. There's another peculiar thing here, which is called emergence or emergent capabilities, which is the fact that accuracy seems to pick up suddenly at a specific scale. Okay, so people have been really puzzled about this, like why is it that we get sort of nothing up until a certain point and then it picks up? Okay, So here's an observation we made with Ricardo Dominguez Olmedo, and Florian Dorner. We fine-tuned each of these models, on multiple choice questions that are similar to MMLU. We don't train on the test set, of course. We just pick like multiple choice questions that look similar to MMLU, have the same prompt style. And here's what happens. The two lines collapse after fine-tuning. And in fact, you get the same amount of accuracy for the same amount of compute, okay? So the performance per compute equalizes between new models and old models. And moreover, emergence disappears. So you can predict model performance at much smaller scale. So what used to take about 10 to the 22 flops to detect, now you see at 10 to the 21. So two things happen. The two model families collapse in terms of their scaling laws, and accuracy becomes predictable at much smaller scale. So this was striking to us because somehow it has pretty far-reaching sort of conclusions, right? So let's think about what this means. What this means is that a small amount of task-relevant data, if you just fine-tune models on a little bit of like task-relevant data or benchmark-relevant data, it has a really large effect on benchmark results. And actually what's going on is that newer models were just trained more on task-relevant data. They had more knowledge about the benchmarks that they were going to be evaluated on. And we investigated this a little bit more closely, and we saw that many model families of the newer models, they actually include the sort of MMLU-style prompts in the pre-training data. So they were actually better at like question answering from the get-go because they knew that they were going to be evaluated in MMLU, so they made sure at training time that they understood the prompting template used in MMLU. And other model families like Gemma, Llama 3, the most recent open source models, they actually select the kind of data mix that you train the model on based on benchmark results. So you see what data mix gives you the best benchmark results to actually get better with the less compute. Okay, so we call this paradigm, what that we're seeing in practice now, training on the test task. People know what they're being evaluated on, so they're making the training data look more similar to the test task. We call this training on the test task. And so training on the test task, we argue, is a major confounder in evaluation, model evaluation, and also claims of emergent capabilities. So what do? Is this like the end of evaluation, or can we still compare models fairly? Well, it's kind of interesting because training on the test task is also its own best remedy, okay? So we sort of make this proposal that you can actually fight fire with fire, and you can give all models the same task-specific fine-tuning data before you evaluate them, okay? So instead of evaluating the models like out of the box, you actually fine-tune them on the same stuff, and then you compare them, okay? So you compare models after fine-tuning, not before fine-tuning, and that actually fixes a lot of the issues with model evaluation. It's a little bit like altitude training. Instead of like trying to prevent altitude training, you just say athletes can use altitude training. You're allowed to do that, okay? And actually, in fact, please do it. If it's effective, why not do it before you go into the competition? All right. So this is training on the test task, and it's both like a problem that you stumble into when you try to evaluate these models, but it's also its own best solution. So in some sense, it's both a problem and a positive result. So I'll end on something that's a little bit more speculative, and that's the question, can we sort of evaluate models that are just coming out in the case where the models that are being released are actually better than experts, okay? So new models can exceed human expertise, and as a result, expert evaluation is either very costly, we would have to hire Terry Tao to evaluate these models, or it's very difficult, and it's not even clear what capabilities we're trying to evaluate and so on. This is called the evaluation frontier, so new models that might exceed human expertise, and it's an increasingly big problem. And so what people have proposed as a remedy is this paradigm of LLM as a judge. So you're trying to use existing strong models for evaluating new models that come out, okay? And so the major issue that you run into with this is that models have strong biases. They have self-preferencing biases, so they tend to like their own output the best, okay? So whatever the judge model is, it tends to like its own output the best, or the output of similar models. And so there's been a really interesting proposal to fix this issue of model bias, where you use a few expert labels as gold standard, together with many model predictions, and you combine these like ground truth labels with the model predictions for sort of an unbiased evaluation. So you use the ground truth labels to unbias or debias the model predictions. And the way you do this is very simple. You basically just compute the mean on your ground truth labels, and you subtract it from the mean of your model predictions. And so that has an effect of making the evaluation unbiased and reducing the variance of your estimator. Okay, and so this is seen as like a way of fixing the issue. But what we show in a recent theorem is that at the frontier, where the models that are being released are at least as good as the human labels, the optimal debiasing method is no better than using twice the expert labels. So it gives you some gain. It's a factor 2, but never more than that. Okay, so let me wrap up. I talked about the ImageNet era and what we learn about benchmarking from it. The iron rule has both internal and external validity, at least empirically, that's what we're seeing. And we know much more about the former than the latter, so if you want to do theory, the latter case is very fascinating to me. And we saw that good data, clean data, is not necessary for model rankings. Okay, so we can compute reliable model rankings on noisy data. Then we moved on into the new era of language models, and we saw that multitask benchmark diversity comes at the cost of stability. Dynamic benchmarks may stall. We don't know what the right way of doing it is. Training on the test task can sort of deconfound model evaluations and give you more reliable model comparisons. And finally, LM as a judge is never better than twice the human labels. Okay, so that's it for today. This is what I call the emerging science of benchmark. ML is anything goes plus the iron rule. Our intuition about benchmarks often fails. And if we're going to proceed this way, we sort of need a more robust science of benchmarking and make sure that this actually works. This is both like empirical and theoretical, as you saw, and I think it gives you lots of really interesting, well-motivated theory problems to work on, and a lot of interesting empirical phenomena to study. I hope you'll join this effort, and let me thank my team in Tübingen. This is the wonderful group that I'm very grateful to work with. We wear these yellow shirts in the workplace, and that's all for today. Thank you so much.
Last slides you had on kind of using LLMs as judges of future models. I mean, when you first wrote it, it was kind of very non-intuitive to me, like, how could something judge something that's more powerful than itself? But then I realized in theory, we do this all the time. The definition of NP, I can verify but not. Right. Is there any actual connection between like proof systems, interactive proofs and so forth, and this kind of thing?
Yeah, so I don't know to exactly this problem, but there's a recent work by Guy Rothblum and Shafi Golbas and others maybe on self-verifying language models. So language models sort of verify their own output. And they use sort of like interactive proofs during the training to make sure that what you generate is efficiently checkable. So that's one way you could proceed by, in the case of well-defined things like math questions, you ask the language model to generate it in such a way that you can verify very easily as correct or not. So I find that very interesting. But yeah, I think it's, in principle, there's no sort of theoretical reason why computationally less powerful mechanisms couldn't evaluate more powerful mechanisms. So there's no sort of like complexity theoretic impossibility necessarily that I see. But it's an interesting thought.
Hello, thank you for your great talk. When you prove that like the majority rule is always better to have more, to go over more data points than to actually reevaluate the same data point, you talked about it as if it was something completely surprising, but it doesn't feel as surprising to me. I think that is the point that like if you know the probability of your label being correct, you can mathematically correctly correct for that. Why do you think, according to you, so many people thought of the other way?
So of course, people's intuitions are different, so you might have the better intuition here. So my intuition is, yes, on some level, having simply more data points that are independently sampled is good because you hit that region where the classifiers differ more often, right? So that's the case for sampling more often. But given that you hit that region, the errors in that region also hurt you more. And actually the conjecture is like, or the theorem is arbitrarily close to being false. So if you like numerically simulate it, you get in very different parameter regimes, you get arbitrarily close to it being false. So it's actually like a very subtle claim because there are these different parameter regimes where the theorem comes close to being false. So, maybe you see like an easier way of proving this, but it wasn't intuitive to me. And actually, the fact that it's so tight in many different places, is maybe an indicator that it's not completely obvious. Thanks for the question. Okay, sorry, I forgot to look this way. Okay.
Hi, thank you for the very interesting talk. I have a question regarding maintenance of the rankings of the models. How does it relate to no free lunch theorem?
Interesting question. How does it relate to the no free lunch theorem? Yes, there's some, I don't know of a good connection. There's some, obviously this can't be true at like arbitrary generality, right? So there's some reason here that this is happening, right? So there's some reason why model rankings transfer. And I don't really have a good definition of what's like a data set that's sufficient for this to happen, right? Like, what is the thing that maybe rules out sort of the no free lunch theorem, right? Like why, what is the thing that data sets need to, the property that they need to satisfy so that you get this kind of stability of model rankings? I don't know. I don't have an answer. So that's a good question, yeah.
Thank you.
Thanks. Yeah, maybe step up to the microphone. We'll take Misha in the meantime, yeah.
I guess my question is actually related to that one. The fact that the ranking are transferring to this seemingly very different data set indicate that there is some sort of really remarkable alignment between the structure of these models and something which happens in the real world, some property of the reality. Any sort of
I think you're headed in exactly the right direction. I actually think that this phenomenon is specific to image classification. It's specific to classification, and there's actually a lot of like mileage you get out of classifying things. So classification is sort of like underappreciated as a sort of source of external validity. And the other thing has to have to do with like images, right? And the fact that like somehow it's a there's sort of an optimal solution, in some sense to image classification, which is something like the human visual cortex or something that is like very good at image classification. And all these models sort of approach that, right? And so there's something specific about image classification that's missing in these language model things where we don't see them, right? Because you don't get the same ranking for like math and sentiment analysis, right? So we don't have this kind of transfer between these different tasks and multitask benchmarks, right? And so, but what that is, I don't actually know. And I think this is like one of the crux with all these things. I think that's really the missing piece that we're not understanding. So, yeah. Thank you. Good question. Please think more about it. I want to hear more from on this. Thanks. Okay.
Thanks for the stimulating talk. And I have a question about constructing maybe more intelligent benchmarks. So as we know, as benchmarks are getting more and more complicated, it's often difficult to understand what is really going on under the hood. For example, if you ask an LM to solve a very complicated mathematical question and you use very fancy prompting techniques, it seems that we have no idea what is really going on other than just scaling up the model. And there has been a lot of debate. People are arguing whether the model can do reason or not. So it seems to me that it's sort of difficult to either prove or disprove those claims. So in order to resolve this issue, can we maybe devise more intelligent benchmark data sets, maybe making more detailed measurements beyond just reporting the accuracy?
Yeah. So this is a great question, and my answer is, in fact, we should do the opposite. We should have less intelligent benchmarks. Okay, so there's two ways to think about what the purpose of a benchmark is. Right? So one goal that you might have with benchmarking is to measure capabilities. Right? To say, would this car drive in the real world, or would this be a good like customer service representative, and so on. Right? That's sort of like the use case evaluation where you really care about the capability. What I sort of like, the more modest goal with benchmarking is what I call sort of like a no regret guarantee, which is that if you're going to go and you spend like a year developing some application, you want to know what's the best model to start from. You don't know, like, you don't care how good it is at your application. It might work or it might not work, but you want to have no regret in the sense that if after a year of working on it, it doesn't work, no other model would have worked either as a starting point, okay? So this is what I mean by sort of like model rankings. You want to know like what's the best model off the shelf to start from for solving whatever application you want to solve. And what you really want to avoid is that like after putting a lot of effort in trying to solve your application, you find out that you should have started from a different model, right? And so that's in some sense like a more modest goal that like benchmarks might satisfy. And for that, maybe simpler benchmarks are actually better. Like maybe like making them less intelligent, you know, like ImageNet is in some sense much less intelligent than ImageNet, much less sort of rigorous in its creation. Maybe that's even better from the perspective of like identifying the best model to start from. But yeah, the different thing is when it comes to measuring capabilities, that's a different story. And I think we should begin to distinguish between these different goals of benchmarking. Are you trying to rank or are you trying to measure capabilities? These are not the same and we're going to get different answers.
Thanks.
Yeah, thanks. One more, okay.
Is there any like theory proving the dynamic data set is better than the static ones? Also, can you comment more on the open direction of the dynamic or interactive benchmarks?
Yeah, so I mean, definitely look at the paper. I think, you know, it's a good question how you want to compare static to dynamic, right? So, because there's some sort of like cost argument, right? Like a static benchmark is cheaper and you could sort of take more data points. And so it's not even clear how you do like an apples to apples comparison with static benchmarks. So in our case, you know, it is, in our theoretical model, it is better than like a single round, right? 2 rounds are better than a single round. So it's better than a static benchmark. But it's not clear that this is the right comparison to static benchmarks, because you could also just take a much bigger static benchmark in practice and instead of doing the dynamic benchmark. So maybe a great question to ask is like how do you even compare like when you should do what, right? Okay, we're over time, but thanks so much for the questions, appreciate it.